Professor? Hello?
Yes, yes, yes.
Yeah. Professor?
Yes, yes, yes. Yeah, I'm trying to switch on my video still. Yes.
Yeah.
Yeah.
Sir, Subramaniam sir, am I audible?
Yes, ma'am, you are audible.
Yes, ma'am.
Thank you.
Audible.
Professor.
Professor Dattatreya Latte, sir, able to hear us? Professor?
Professor Latte, sir.
Professor, shall we start, Professor? I think.
Sir, I think he left. He will join again, sir.
Yes.
Again. Yeah.
Okay.
Yes, Professor.
Hello. Hello.
Hello, Professor.
Yeah, can you hear me now?
Yes, Professor.
Yes, Professor.
Okay. I have joined now, but still, I think there is a. Yeah, now my video is started. Yes.
Yeah. Welcome, Professor.
It's fine, sir. Welcome, Professor.
Yeah. Thanks.
On behalf of Department of Physics and SRM Ramapura campus, I welcome Dr. Dattatreya Latte, Professor. So thank you for giving consent to deliver the talk in our national level online FDP, sir. Thank you so much, sir. Dhanasekar, sir, shall we?
Yeah, sir. Shall we start?
Yes, sir.
Yeah.
So, good morning to one and all present here. We are happy to invite you for the. Sir, am I audible?
Yeah.
Yes, sir. You're audible.
Yeah.
Yes,
I'm
madam.
happy to invite you all for the session 4 and day 4 of our national FDP on advanced computational and experimental research in physics. So today's session will be handled by Dr. Dattatreya Latte, Professor and Head, Center for Nanoscience and Nanotechnology, Amity University, Mumbai, Maharashtra. Sir, now I request Dr. M. Dhanasekaran, sir, to introduce our resource person. Sir.
Thank you, ma'am. Good morning, everyone. So I welcome you all for this day 4th 1 week national level FDP on advanced computational and experimental research in physics. It's my privilege to introduce Dr. Dattatreya Latte, sir, Professor and Head, Center for Nanoscience and Nanotechnology at Amity University, Mumbai, India. Professor Latte has obtained his PhD degree in physics from Savitribai Phule University, formerly University of Pune, India in 2008. He did a DST Nanoscience and Nanotechnology postdoctoral fellow with Professor CNR Rao at JNCSR Bangalore in 2008 to 2010, and then worked as a postdoctoral fellow at Material Science and Engineering Department, Northwestern University, USA, with Professor VP Dravid. So Dr. Latte received many awards like a prestigious Ramanujam Award at the CSIR National Chemical Laboratory, Pune, and received Young Research Scientist Career Award from Science and Engineering Research Board from Government of India. He is also a fellow of Maharashtra Academy of Science and a fellow of Royal Society of Chemistry, London, UK. He was listed as a top 2% scientist from world by Stanford University, USA in applied physics in November 2020 and October 2021. His current research work mainly focused on the development of 2D hybrid materials for nano and optoelectronic devices, energy generation, and storage application. He is a leading expert on Raman spectroscopy to characterize a wide range of carbon and inorganic 2D TMDC based materials. So Dr. Latte has published more than 210 research articles, edited 2 books, filed 18 patents, and also a member of various scientific society across the world. So now I request Professor Latte to deliver his presentation. Sir?
Yeah, can you hear me?
Yeah, yes, sir.
Okay, just give a moment so that I can share my screen. Okay.
Yeah.
Yeah. Tell me when you are able to see my screen. Okay.
Yeah. Yes, Professor.
Yeah. Yes. Can you see my screen?
Yes, Professor. Yeah, it's sharing.
Yeah.
It's sharing. No, it is not visible. It's started sharing.
Okay.
Professor, your screen has been shared, but no, nothing is visible. Now it's okay.
Yeah, now it is visible. Now it is visible.
Okay. Okay.
Professor, could you make it as a full screen, Professor?
Yeah. I'm just
Yeah.
It's coming, right? Okay. It's full screen?
No, Professor.
No.
Or maybe it's full screen mode.
On the bottom.
Yeah.
I've done the display.
Yeah, I have done it already. I've done it already.
Yes.
Can you see this full screen now?
No, Professor.
On my screen it shows full screen.
No. Maybe it's not visible for us.
Yeah, I don't know. It's slightly net is slow at my end. Okay. Now it is full screen.
No, Professor.
No, Professor.
But I think I have done it. That button I have clicked. So on my screen, at least it is on full screen mode.
Okay.
I can do it again.
Yeah. Can you try it again, Professor?
Yes. My screen is at least visible, right?
Yeah, screen
Yeah,
is
it
visible,
is.
but it is not enlarged.
Okay. I will just make it now. Yeah. Now it is.
No, Professor.
Then I will make my screen little small so that you can at least see the whole presentation. Can you
Yes.
see now presentation?
Yeah, we able to see your presentation, Professor, but it is not in the full screen mode. Please
Yeah.
click. Okay.
Yeah, you can see right. I'm just clicking full screen. Now?
No. Can you increase the resolution, Professor? Magnification. Yeah, a little bit.
Okay.
Yeah, okay.
Now, can you see my full screen?
No, Professor. So only we can see half of the screen.
I think that might be some problem. Okay, then I will zoom it out, right? Slightly.
Yeah.
Just tell me when you are able to see.
Yeah, now it's fine. Now it's fine. Yes.
Okay, Professor.
Yeah, now it's okay.
Now it's okay?
Yes.
Okay.
Now it's okay.
Okay. Thank you, Dr. Zansekar and all colleagues from SRM Institute of Science and Technology for kind invitation. So today I'm very pleased to have a talk on this national FDP on computational and experimental physics. So I'll be talking on more of physics, chemistry, and maybe a kind of technology which we're working since last couple of years. And again, this is based on 2D nanomaterials. What technological things we can do with these 2D nanomaterials? Because 2D material are, since last 10 years is booming kind of field, and where a lot of people are working because it has certainly a real technological applications. Okay, I'll just start my talk with this quote by Swami Vivekananda. Experience is the only source of knowledge. In word, religion is the only science where there is no surety, because it is not taught as a science of experience. This should not be. And what happened? There is always, however, a small group of men who teach religion from experience, and science doesn't come from experience. They are called mysteries, and these mysteries in every religion speak the same tongue and teach the same truth. This is the real science of religion. Why I'm telling you this? Because why today China is #1 in all the field. Why science? Because science and technology made really China superpower. Those who are interested to read how China become #1 today because of science and technology, they can read this article published in Nature a couple of years back. And this is very interesting to show how China has made the progress in all the fields. When you think about small kid going to school, college, wherever, India situation, wherever you go, we'll see the board by politics, all kind of advertisement, But in Chinese, I visited China 2 times, and what I find every wall, every poster is based on science, technology, something like that, some painting, all related to science and technology. That's why kids see all these things, these posters, wherever they go garden, they go anywhere, they go to school, they go anywhere, they see all these slogans, they see all these pictures. This is one of the picture cartoon which they can see on the walls of the roadside. So that is the inspiration comes from the kid, and when they grow, they do really science and technology. So that is also one of the reasons why today China is #1 in science and technology. So let me thank all this funding agency who has largely supported my research since last 10 years. Let me thank many of my collaborators from India and abroad for all their support and help, since most of them are my PhD student also. They have graduated and they are working as a postdoc or faculty in some of the universities. Okay, those who are interested, actually, they can submit these 2 journals, which is AIP Advances and another journal, Royal Society Open Science, where I am actually editor of these 2 journals. You are most welcome to submit your research related to physics, chemistry in these 2 particular journals. There are 2 more journals which are from IOP, Electronic Structure, and IOP Synod. These are new journals. So this is the 3rd year of this journal, and new impact factor of these 2 journals likely to be around 3. So you are also most welcome to submit your research in this new IOP journal as well. Okay, what are the facilities we have in our group? We have this kind of optical microscope. We have chemical vapor deposition system to grow various kind of nanomaterials. Then we have gas sensing system. We have this photolithography system, which we have developed in-house in our laboratory, through which we can develop fabricated devices in the scale of 100 to 200 micrometer. And these are the stainless steel. So in one shot, how we can rapidly pattern the devices. Within say a few hours, we'll get at least hundreds of devices based on this stencil mask. Also, we're working on a supercapacitor and battery and the setup which is needed to test all these things, which already we have in the laboratory. We have electrical characterization and again the low temperature measurement setup in our laboratory. These are again made by in-house joint the parts from taking the instrumental. Again, we have setup for hydrogen generation. Hydrogen, today we are talking about the electrical vehicles. That, but in another 20 years, everything will be on hydrogen.
Professor, sorry for the interruption.
Yes.
Slides are not moving. Slides are not moving.
Okay. I think then I will stop sharing and then reshare it again. Okay.
Yeah.
Okay. Tell me now if we can.
Yeah.
Can you see my screen?
Yes, Professor, but you please click the PPT.
It's not.
Can you click your PPT?
Yeah.
Yeah, I can see your desktop.
Okay.
Yeah, can you click your?
Yeah. That is it is slow from my side. Yeah. Yeah. Can you see my screen?
No, Professor. We can see your desktop only. Can you click your PPT, Professor?
Yeah. I'm just clicking. Yeah. Can you see my PPT?
No. No, it is not visible for us.
Yeah. Just one second.
Professor Latte,
Yeah.
is it possible to share your PPT to Dr. Dhanashekhar?
Yeah.
Will share the screen.
Yes.
If you find some problem,
Yeah. No. Yes. I think I'm now should be fine. Can you see now?
Yeah, now it is visible. Now it is visible, Professor.
Okay.
Just to change it, change the slide.
Yeah. I'll
You
just
can
change.
see.
I'll just make a full screen as well.
Yeah. So kindly change the slide.
Yeah. Can you see it now?
Yeah, it is visible, Professor, but it is not moving.
Now?
No, it's not changing.
No,
the slide. Slides are not changing. Yeah. Now it is fine. Now it is fine. Can you reduce the magnification?
Yeah.
okay.
Right?
Yeah. Now it's fine. Now it's fine. Clear.
Okay. Yeah.
Okay,
Thanks.
Yeah. Thank you. Yeah.
Okay. I just talking. Sorry, I was just talking about this paper, which is published in Nature, about science and technology. How science and technology really made China superpower. So those who are interested, they can now go through this paper published in 2019, and this very interesting paper to read. And there are many citations to this paper as well. So you can find very interesting science and technology from China. Okay, let me thank funding agencies who has largely supported my research since last many years, including CSIR, DST, then DAE, DPT, and all other funding agencies. Let me thank my collaborator who has largely supported my research since last more than 10 years, collaborators from India as well as collaborators from abroad as well. So I was just talking about these two journals, AIP Advances and Royal Society Open Science, as well as there are two more journals from IOP, that is Electronic Structure and IOP Synode, where you can submit your research related to physics, chemistry, science, technology, environmental science, and likely impact factor of these two journal, bottom two journal, Electronic Structure and IOP Synode, is around 3, predicted to come this year. And the facilities which I was talking, we have these facilities in our laboratory. We have optical microscope, we have chemical vapor deposition, we have gas sensor system. Chandrasekhar, can you tell me that you are able to see my slides?
Yes, Professor. Yes.
Okay, great. Okay, so we have this benchtop lithography system. We have a potentiostat for testing of supercapacitor and battery. We have electrical characterization system. We have a low temperature setup measurement. And then I was talking about the next fuel of the generation. I think it's hydrogen generation. Also working on hydrogen generation. We have funded project on hydrogen, and this is actual experimental laboratory setup which we have made for hydrogen generation. Again, of course, this is hydrogen generation is from H2S splitting. We split H2S into hydrogen and sulfur. Hydrogen as a fuel and sulfur is also some useful product for the agriculture. And then we have also set up for solar simulator and solar cell IV characterization system in our laboratory, so that we can measure the kinds of parameter which is needed for solar cell, like efficiency of the cell, fill factor, short circuit, current density, open circuit voltage, and their other related parameters also we can measure in our laboratory. So since couple of last years, we are working on 2D materials. So we look all these 2D materials in perspective of physics, chemistry, material science, engineering, where we really develop a technology where we can design a device and then we can test through physics point of view, or maybe depending upon application, what application we are looking, what technology we are looking. For example, maybe there might be some technology related to medicine, right? Can we use these kinds of devices for medical application? I will see you in a couple of minutes some example how this 2D material based science and technology can be used for real-time technological application. Even what we can do with biological application or microbiology, biotechnology applications. Maybe some of these materials are very good for antibacterial, bacterial applications, like gram-positive, gram-negative bacteria. And this type of study also we are doing in our laboratory. So what we are looking for energy project. So we are also a separate group, a subgroup which are working on energy, and again based on 2D graphene hybrid materials. Then we are looking for solar cells. They were looking for the hydrogen generation. We are looking for materials for industry demand, because today's in era, academic research is no use if we are not collaborating with the industry. Because again, at the end, we have to transfer all the technology to the industry so that they can produce in mass scale, and then it will be a real societal application. Also working on, again, these batteries, supercapacitor, fuel cells, again, depending upon the demand of industry. We also do this material technology coating. Some of these materials are useful for defense application as well. So when you talk about the smart car or future car, already there is a car by Google, driverless car by Google, right? So it's America. But there is no surprise, in another 40-50 years, we have a driverless car in India also. Because today all roads, all houses have been mapped by Google, right? So mapping is very good done. But now if you want to have a car, when you go to Chennai, any place, Delhi, Mumbai, our traffic jam is so huge, right? So because when you have technology, right, there is actually a project by MIT, Government of India. Can we have a driverless car? Can we have automatic traffic, so that depending upon traffic, which road there is a less traffic, you can automatically move. Anyway, Google shows all these things, but it should be a more systematic, right? It should be a more kind of in line wise, so that see, again, all these sensors play a very important role. So for example, if you want to a car of future which is driverless, the kind of sensor which needed. So these are the list of sensors which is needed for this driverless car. Again, when we talk about this kind of any kind of sensor, so always there are some challenges. Which kind of material, which is very important physics point of view. Then how we can integrate this material, sensor, device, and all these things. How we can do signal processing. Then a lot of engineering, electronics engineering, computer science is also involved in this kind of technology. Again, how we can fabricate these devices on large scale. Again, once your device is ready, but then it has to be mounted on the some kind of chip, and then we want to sell these devices in the market. Then of course we need to do the packaging of all these kind of devices. Now, talking about the healthcare system is very important because since last 2 years when the COVID has came, now everyone has become more aware about the health and all these things, because this health is very important. And the kind of devices which are working since before COVID, they were low cost sensor, flexible, and self powered. This is very important. What happened normally, once we keep device, we need to change battery and all these things, and then by the time device does not work, right? So we need a kind of a device which should be self powered. And then it should be a flexible and it should be wearable. So any person can wear. For example, I want to develop a sensor which can detect cardiovascular disease, any kind of thing. So device should be very flexible, and wearable, as well as self-powered. And very most important in context of India, it should be a low cost, right? Because cost is very important. If cost is very, very high, then we are not going to afford all these kind of devices. So when you talk about the sensor which is needed to diagnose any kind of disease, so these are the type of sensors which can measure. For example, we can measure electrical signal. We can also detect the kind of diseases by optical sensor. Then, for example, we want to develop kind of, say, chronic kidney diseases. For example, you want to detect how much is the ammonia split. Then we need to do the analyze by mass and all these things. We want to, for example, detect how much, whether person is diabetic or not. So we need to detect how much is the concentration of that particular element or that kind of molecule solution in your body. And this can be again detected by this kind of sensors or technological devices made through all these devices. So why wearable sensors are very important? Because wearable sensors almost can detect all parameter which is needed. You want it to be healthy, right? It can be detect enzymes. It can detect all any liquids. It can detect what is the sequence of your nucleic acids and all these things. It can detect antibodies. Not only detect in antibodies, it can continuously monitor your body, right? And then now what happened to your body, what is there up and down and all these things. All the time it can measure temperature, all the parameter which is mandatory needed. When you go normally to hospital and do test, all the parameters it will continuously monitor. And all these devices, again, it is flexible, low cost, variable. So, and one connection is given to your mobile, and you can continuously monitor, like you're monitoring weather or you're monitoring news channel, right? Continuously. So same thing, you can continuously monitor your body parameters on your mobile itself, so that you can see how much is the temperature continuously. You can see all the parameters which are present in a body or which is needed to be monitored from the body. Okay, for example, this old person who is walking on the road, and what happens, sudden he has attacked and he has fall down, and he has already this kind of wearable device on his body, and this is rechargeable, self-powered, because they have nano generator, and this kind of nano generator give continuous power and device is working. And the moment he has fall down, so there will be again it is connected to his mobile, and then mobile signal will go to emergency vehicle, one message will go to his family, one message will go to clinician, and then this emergency vehicle will go to the person, family members also rush to the person, and doctor will also know, okay, this this type of person or this person has been fall down, and he has also his all the data, because all the data is already collected in the mobile or whatever system, internet, and the doctor will see, okay, what is the temperature, what is this BP and all these things, all the parameters, and depending upon that, he can suggest medicine or he can give a treatment, and then patient's life will be saved. Because when the moment the person fall down because of the heart attack and all these things, they don't have much time. So that initial time is very important. We can do all these things through science and technology. Really, we can save a lot of this kind of persons who has heart attack and a similar kind of diseases. For example, what are the this VOCs? Their concentration in healthy person through exhale breathe. So this is another very simplest method to find out whether person has the kind of cancer or not. So these are the concentration of various chemicals or which are present in the body in the terms of PP. For example, toluene in the body is 1.4 to 37.2 ppb. Similarly, acetone, methanol, benzene. So these are the concentration which we can detect through our exhale breathe. So what is the advantage? So can we detect lung cancer based on these parameters which are present in the body? What we need to do? We need to just collect exhale breathe, and that exhale breathe can be transferred into a chamber, gas chamber. It's again similar to gas sensing system, and then we can actually detect how much is the concentration of all this acetone, methanol, benzene, hexene, heptene, ethanol, whatever alcohols in the body. And depending upon the concentration, we can actually tell that the person has lung cancer or not, or is healthy or not. So this is very simple method to detect. Again, this is based on 2D nanomaterials, graphene, MOS2, and all kind of materials. Okay, so so this is the parameter just before COVID-19, that each year national healthcare expenditures are rising 2% faster than the GDP. But after 2020, it is more than 10%, because how much we are aware about our health system and health awareness. Again, gas sensor, all kind of gas sensor, the demand on all these sensor is increasing. All sensor, all technology which is related to a body, they're increasing. You see, 2006 parameter to 2028. See how therefore it is very important to work on these areas, because demand, the market is increasing continuously. And why it is important? Because today we're talking about the flexible devices which are based on nanomaterials. Why based on nanomaterials or 2D materials? Because they are flexible, they are wearable, and they are accessible, as well as they have high sensitivity, high selectivity, and all these parameters. So as parameters, we can continuously monitor through these wearable devices. For example, we can always monitor using sensor like your ECG, then skin temperature, elasticity, skin strain, pulse rate, blood pressure, blood oximetry. What is the oxygen? Because this is in COVID-19. What is the oxygen? Is very important. Oxygen level is very, very important. So all these parameters can be continuously monitored or measured by using these wearable sensor kind of dish. So there are many other parameters. You can see many other parameters that also can be continuously monitored by using this type of devices. Again, instead of just wearing the small this kind of watch, you can wear the smartwatch, right? So this also you can tell that how much is your heartbeat and all these things. All the parameters it can continuously recorded as well as monitored from your body. Again, this is based on 2D material, 2D technology devices, and they are already in the market, but still cost is very high, and then everyone cannot afford. And once their cost is slightly low, then of course everyone can afford all these kind of devices. Again, there is a might be heard about this is a ring sensor. So this kind of ring sensor actually continuously monitor your body temperature and oxygen level. So this is based on simple physics of photoconductor, based on this photoconductor measurement. So you can measure blood pressure, pulse, we can put into a ring, and then there will be a vessel wall displacement, and we can monitor the blood volume changes because of this photoelectric method. Again, this is a simple based on the photoresistor, and we can monitor the body temperature as well as oxygen level by using this simple ring sensor. Instead of wearing the gold ring, I think now time has come to replace this gold ring into this technological ring, so that you can have a healthy India, right? Okay. So what are other technological devices, wearable devices already in the market? So these are some of these devices. They're already available in the market. For example, we can wear and then we can continuously monitor many other parameters which are essential to monitor for our body. So these are some of the products which are there. Again, I said this is just beginning, and many more things will come in another say 5 to 10 years. For example, devices for lung cancer, smart step, then many kind of all these things, devices for detecting cancer, blood cancer, and all these things. Many things will come with these technological advances. Again, this also fitness become very important monitoring parameter, and this will also come in another couple of years. And again, this is based on feedback, and anyone can wear it, and anyone can monitor the parameters which is needed to monitor from your body. Again, these are the smart wristwatch. Again, this again same principle. Instead of wearing this principle, wearing this smartwatch, we can use a nano technological watch, so that you can have your all body parameters all the time with you. Again, so these are the flexible devices. Again, these are based on nanomaterials. Nano, one of the parameter is that we can change the color. So color of the device and color of your skin can be the same. You can see this is just wearable sensor, so that it doesn't have any side effect, and we can continuously monitor your body parameters and continuously given to your mobile, or it can be connected to internet, so that anyone can access your body parameters. Your doctor can access, your family person can access, anyone, those who has given access, they can access your body parameters all the time. So what are the things, what do you do in nanomaterials or 2D materials? For example, you want to make a stretchable, transparent and ultra sensitive sensor. For example, we want to detect emotion. So what is the physics? Simple physics. So we have, again, this is based on carbon nanotubes and graphene. We have some polymer, like for example, these are based on PDMS coating and carbon nanotubes as well as graphene. And so this is, we measure resistance. For example, a girl is laughing here in figure A. You see how much is the resistance change. You can see resistance change, right? You can see here from 0 to something 0.4. This is just ratio of change in resistance to original ratio. How much is the ratio? And same thing, the same device. Again, the girl is crying. You see how much is the change in resistance. So this again matter of research, that why there is a large change when girl is crying and instead of girl is laughing. And again, where you have kept this device. For example, I have kept the device at forehead. I have kept this device near the mouth. So these are also parameters to be studied, and they give the kind of resistance change based on where you have kept this sensor forehead. Again, so they are completely invisible, because again, these are based on nanomaterials, 2D materials, and your device color can be as same as of your skin screen, and you can monitor emotions all the time. Even some person is just standing in front of you, it doesn't show any emotions. You think that, but there is a change in emotions that can only monitor through the kind of technological devices it has, because you can see how much is change in resistance, right? He's laughing, really laughing, or he's really crying, right? That you can actually really understand from this kind of devices. Again, so we can go through many approaches. One of the approaches, okay, can you basically stretchable electrometric or nanocomposite based devices? Yes. Again, what kind of parameters? So what kind of physics we look? Actually, we can look this piezoelectric material. We do parametric devices, piezoresistive, chemi-resistive, thermoresistive, temperature, photoresistive based on light and all these things, electroactive, right? And all these things. So basically we combine all these nanomaterials, make devices. So they should be transparent, they should be electrodomestic, they should be stretchable and all kind of thing. So at that, what we see actually, so that these devices are stretchable, they are all are transparent, they are all ultra sensitive, they are all self-powered backups. They will be based on the principle of this nano generator. They can generate power themselves and the device will active all the time. So for example, I can put a nano generator to my shoes, or I can, depending upon your movement walking, right? So device will start charging. So it will generate this kind of small voltage, and that small voltage we can store, and then that can be used to charge your device or to keep your device active all the time. Okay, so for example, these are some of the stretchable transparent device which can detect the strain sensor for emotion detection. How device has been made? Okay, see this is the arrangement of device. You know, devices based on PDMS, carbon nanotubes, graphene, and you can see the parameters we can measure. Suppose the device is bending, right? So you can see how much is the resistance change. Okay, how much is the change? 1.6%, 2%, 2% or 3%. You can see how much is the change in resistance. Again, the device is stretchable, right? The moment you come back, the stretching, they will get the original resistance. So that kind of devices we needed. Again, you see the transmittance, almost 60% transparent. Your device is transparent. You can see now completely that building right here. And we see you can measure strain. If you go apply strain, depending upon 10%, 20% strain, 100% strain, you can see how much is the change in resistance. So this is very important. Device should be stretchable, transparent, and ultra sensitive. Small change on device surface or anything happens, small crack, anything on building and everything, it should detect. So that is ultra sensitive. So that is very important parameter if you want to measure the kind of devices. Then what kind of other parameters we can measure? You can see these are some of the cyclic stability. So you can see here device kept on forearm, right? So almost transparent, right? You just see the body color, just instead you can see the two dot, otherwise it is already kind of transparent device. And then cyclic stability you can measure, you can use for 5 years, 10 years and all these things. So there is no dramatic change in cyclic stability. So this is very important parameter that device should work on all these things. And then basically the kind of self-powered, again I just mentioned the piezoelectric device, it should have very good cyclic stability and all these things, so that you can use many cycles, charging and discharging. Basically when you talk about these technological devices, when we integrate these devices, we need a lot of help from software, computer science, circuit, telecommunication, because device has to be communicated with your family, device has to communicate with doctor and all. And then materials, basically material science, engineering, physics, device fabrication, device measurement, parameter optimization, biomedical, because the device should be compatible to your body. And at the end, integration of all these sensors to make a final product based on these technological advances. Okay, so what we are doing actually, we are growing all these 2D materials. Once we have identified the materials, for example, I have identified 2D materials with 3 layers as very important material now for technological advances, for example. And then we can start growing of this material. Then once we have grown materials, then to optimize the thickness of the materials. For example, we optimize thickness, that 3 layer, whatever, 4 layer or 6 layer, MS2 or any kind of material, it's very good for this technological application. Then we'll go for these optical properties. Once the device is successful in this optical properties measurement, because you want device to be transparent, you want semiconducting material because you have to monitor device to be on, off all the time. Then basically we need to do mechanical properties measurement. And then once the device test pass this all tests, then we go for electronic properties and final device fabrication and their optimization. Okay, so what I'm going to talk about in another maybe 30 minutes, that the kind of materials we have gone, graphene like materials, why graphene is more important today, and what can we do with graphene like 2D materials, and what can we do if you can make a composite, we can make a hybrid materials based on graphene and 2D materials. Okay, So I'll just give a brief introduction of graphene. I know everyone here, they know about graphene. It's a monolayer of sp2 bonded carbon atoms. And what you can just a graphene sheet, this is a benzene ring connected to each other, make a complete parallel sheet where you can just wrap this kind of sheet, you will get the zero-dimensional buckyball. You can roll this sheet like a paper. You will get one-dimensional carbon atoms. You can stack these papers to each other. You will get the three-dimensional bulk graphite material. Why graphene? Because it is lightweight, it is strong, it is impermeable. You know, one of the property of graphene is can be used to store any kind of gas, right? Any kind of gas, because that is the kind of properties graphene is possessing. Again, it is a transparent, complete transparent, flexible. You can flexible and make it, and then it is thin. So smallest material on the world, right? On the earth, because the one layer graphene thickness is around 0.34 nanometer. So that is the smallest things we can make by this single layer of graphene. And it is highly conducting material, highly conducting material. So these are some of the other properties of the graphene. You know, if I take a graphene, so this is this cartoon shows that if I can take graphene sheet and if I made some pin on the graphene and I can put actually that one elephant on the pin, still will not be able to penetrate that one graphene sheet. So that is the property of graphene, that highly stretchable as well as same time strong material. If we measure Young's modulus is more than 1 TPa. So that is the strongest material. So that is the advantage of this kind of material. Okay, so this is slight physics. I just don't want to go into detail, but you already know that the this Dirac cone, they are just touched to each other, and that make graphene so important and make it semi-metal, because it doesn't have band gap. The conduction band and valence band, they are just touching to each other. That makes energy of electron, which is directly dependent on the wave vector near this Dirac point, and that gives a zero band gap semiconductor or whatever you can, semi-metal. And because of that, we have because of this Dirac solid, we have black strict transport of electron charge carriers in the graphene sheet. The moment we apply voltage to the graphene sheet, it starts conducting. And another, when you talk about the electronic devices, it shows ambipolar behavior. Means we apply negative gate voltage or positive gate voltage, still we have charges in the channel. This can be understood by very simple equation of this energy, momentum, and mass. So this equation gives a relation between mass and momentum. Here, graphene, okay, the moment you apply voltage, so charges like electron moves in a this graphene sheet because of this small apply in voltage. Here, velocity of electron or charges are so fast in the graphene sheet because they sometimes behave like a massless. The actual electron has mass, right? So they behave like massless particle. When m is equal to 0, energy of electron in a graphene sheet is directly proportional to this if you see, that is velocity of light, right? The velocity of electron in graphene sheet is equal to 1/300 times the velocity of light. So quite fast. Therefore, electron mobility is very high in a graphene sheet, right? So how we can make graphene? By this is just by simple exploration. You need actually kind of Scotch tape. You need this HOP crystal, and you need a simple optical microscope. So you take this HOPG or graphite crystal. You need this tape, and you of course you need a SiO2 Si substrate. What you need to do, you have to take this tape. We have to put the tape onto this HOPG crystal. You put slight pressure. You take out that tape, and you can put it on SiO2 Si substrate. You can put small pressure again on the tape. You can take out the tape. You can go to optical microscope and see under the optical microscope what are the color contrasts you can able to see. You can see this. These are some color contrasts to which you can identify whether graphene which transferred on the SiO2 is 1 layer, 2 layer material. Of course, you can do atomic force AFM, atomic force microscopy, scanning plane microscopy. TM. But most accurate measurement to thickness or layer identification is Raman spectroscopy. I will tell you in a couple of minutes. And so these are some of the other optical images where you can identify just by optical contrast whether the transfer graphene layer on SiO2 is really 1-layer graphene or 2-layer graphene or 3-layer graphene. Okay, just see by color contrast. Because of course, these are multi-layer or kind of graphite, because more than 10-layer is like bulk material, right? So graphite kind of thing. You can really see this very interesting or very simple technique to transfer monolayer of graphene from bulk graphite. Even very simple chemistry can be learned, right? You take a bulk graphite powder, you can do oxidation in presence of strong acids such as H2SO4 or HNO3, and you can do it, and then you will get the graphite oxide, right? Again, you do mechanical explosion by just ultrasonication, or you can do thermal explosion by heating the sample in high temperature furnace, right? And then of course you will get the single graphite oxide, right? Then of course you can reduce it by some reducing agents such as hydrogen. You will get single graphene, right? Single graphene. But this is of course in a solution form. And for technological or any kind of application, sensor application, you can drop cost, or you can do coating, any coating, deep coating or whatever coating you want, depending upon the kind of application which you choose. Of course, you can do TM, AFM, and you can measure how much is the thickness of this the grown material or grown graphene. And of course, one of the very powerful technique to identify whether grown or transferred graphene is 1-layer, 2-layer, or multi-layer is the Raman spectroscopy. You see, in this typical Raman spectroscopy of single-layer graphene and this bulk graphite, you can see in this is GP, which is arises because of the stretching of carbon-carbon bond, and this is 2D because it arises again laser frequency dependence, which actually used to monitor how many layers are present in your particular the grown or transfer graphene layers. See, one of the parameters is the intensity of this G band and 2D band. So this also signature that okay, we have actually intensity of this 2D band is 2 to 3 times. Then you can say that this is monolayer of graphene. Also, you can see the pitting of this particular peak. You can able to only pick a single Lorentzian. You can see here there are multi peaks, right, in bulk or more than 2-3 layers. Okay, see, the moment you go to now 1-layer graphene, you see from 1-layer graphene to 2-layer graphene, you see now intensity of this G band and 2D band. Here intensity is nearly similar, and you can see here the 3-layer graphene and 4-layer graphene and 5-layer graphene. So you can continuously monitor these graphene layers. Okay. Okay. Again, Raman spectroscopy become very powerful technique to identify or to distinguish whether the material which we have graphite or graphene oxide or reduced graphene, because you all look same, right? The moment, for example, you have graphite, you can see just do the continuous Raman spectroscopy, and you will get a single peak that is G around 1581 for bulk or pristine graphite. The moment you make it graphene oxide or reduced graphene oxide, you will see a lot of functional groups, right? Defects will induce in the graphene, right? That graphite. So we'll have, in addition to G band, we also have this D band, that is defected to band. So that will around 1363, and you can see this G band, the peak position around 1581 shifted towards 1594. This becomes slightly wider, and this really tells the some physics behind it. And the moment you convert this graphite oxide into reduced graphene oxide, you see this this defect with the intensity of this defect, that D, here intensity of D to D by G ratio, which is larger. So you have already reduced many of these groups, and you have actually a reduced graphene oxide, right? So these are the some simplest technique to identify this kind of material, right? Okay. So what we have done, a technological device application here. So we have, in chemistry, it is well known that this tetrathiophylline, that is TTF, and tetracyanoethylene, that is TCNE. So these are very powerful electron donor and electron acceptor molecule. So what we have done, actually, we have prepared different concentration of this TTF and TCNE, and because they are electron donor and electron acceptor molecule, and pristine graphene is ambipolar kind of device, right? So it shows the conductivity as a electron N type as well as P type. So we thought, can we make this graphene more P type or N type? So by using this simple experiment, we shown that we can make graphene more N-type, or we can make graphene more P-type. So what we have done, we have prepared different concentration of this TDF and TCNE, and we have this kind of two samples, that is single layer graphene, which is transferred by micromechanical explosion. This is another sample which we have in solution form, that is reduced graphene oxide. And what we have done, we have recorded the Raman spectroscopy of pristine Raman graphene or reduced graphene oxide, and we have started adding this concentration of TCNE and TTF. And what we find very surprisingly, that with increasing concentration, we will see with increasing concentration of TCNE or TTF, there is a shift in the G band position. You can see with addition of TCNE, the G band shifts towards the higher frequency side. You can see, and with TTF, which goes to lower side. So this this completely indicate that when you add concentration of this TCNE, graphene becomes more P-type, and with addition of TTF, graphene becomes more kind of N-type behavior. So then because of the what happened here, when you add this TTF or TCNE, so this homo thing, that the transfer of the charges from molecule to graphene, and then if this hemo of the molecule is above the Fermi level of the graphene, you can see the this band, electronic band structure position, and the position be here when this LUMO is this side, this Fermi level is this side. When the charge transfer from graphene to a molecule, if the Fermi level of the graphene is above of the LUMO of the molecule, of course you can see monitor the shift in G band as well as 2D band. The changes are arranged because of this structural change, and then there is a slight shift in the Fermi energy level, and this FWHM also monitored. This also found to be change because of the change in phonon lifetime and all these things. And with this addition of this TTF and TCNE, we also expect that there is a small opening of the band gap, and that is absent in a pristine graphene. So it's possible that a small band gap can be open at between the conduction band and valence band. Okay, we have done the electronic experiment based on this technology. So what we have done, so can you make a technological variable device to verify our conclusion that graphene can be a more P-type or graphene can be a N-type? And then yes, of course, we have used here electron lithography technique to fabricate this kind of devices. Again, these are graphene transferred from micromechanical explosion on SI to SI substrate. We have fabricated the device by using electron beam lithography, and these are kind of devices. And how we can make a device? This is a simple procedure. We can get it on any research paper on internet. That how we can use electron beam lithography to fabricate the kind of devices. And then once the device is ready, so this is optical microscope of single layer graphene transfer on SiO2. This optical microscope of image of the after fabrication, and this is SEM image, and these are AF images of the device you can see. And these are again based on field effect transistor based on single layer of graphene. Okay, so then of course we have done the electrical characterization. So we need to do post annealing, vacuum annealing, so that your device show better performance, annealing and all these things you need to do. And say your pristine graphene device or field effect transistor based on single layer of graphene shows ambipolar behavior, because your direct point is at 0 volt, right? 0 volt, right? So this completely indicate that it shows ambipolar behavior. Now what we have done actually here, so to prove our theme that can you make graphene make more P-type, or can you make graphene more N-type? So again, we have recorded the electrical measurement, so that the pristine single layer graphene, it shows ambipolar behavior, right? And direct point is at exactly at 0. Now what we have done actually, we have started adding this concentration of TCNE, for example, 10 raised to minus 6 molar, minus 8 molar, and all these things. See, with increasing concentration, you can see this, there is a slight shifting of the direct point from 0 volt towards the positive gate voltage. So this completely indicate, clearly indicate that graphene becomes more P-type. So this is the way we can make graphene more P-type, or you can make graphene N-type, and all this. So there are several examples in the literature that Okay, for example, so these are some of the aromatic molecules. What happen? So these molecules bind the single layer of graphene and to the strong pi-pi interaction, and their aromatic rings and the graphene. So it shows the kind of behavior. For example, this is piston graphene, this is TPA molecule, and you can see when you can add some kind of other molecule, you can see whether your graphene becomes more p-type or n-type, and you can monitor again by using single layer graphene. You know, see this G band is very sensitive to surface modification happen on the surface. Any small change happen on the surface of graphene, it immediately shows the change. Maybe shifting, or maybe you can once now this is single layer graphene Raman spectroscopy. The moment you have something on the surface, now there is some defect induced on the surface of graphene, right? So it immediately shows the deeping, right? So that is also kind of signal that we can understand to measure some of the other properties of the graphene. Of course, one of the properties of graphene is sensor. Can you make a graphene a sensor? Again, because there is no band gap. Sensitivity is very good, excellent. Selectivity is also good, but there is the response and recovery. Response is also good, but recovery, because the binding of molecules on the graphene sheet is so high, that binding range is so high, it's difficult to remove these absorbed molecules and all these things. So we have to provide large energy. So we have to put external supply energy, so that you can take out all the molecules bind on the surface, so that your recovery time will be very faster. Again, some of the applications like humidity sensor, we have tested the device for more than 30 days and find that the operation is stable. Graphene is so strong and stable material. It has real application in kind of this sensor. For example, it can be used for flexible touch screen application. It can be used for ink application. It can be used for display application. It can be used for solar cell and battery kind of application. Dhanashankar?
Yes, Professor.
Okay. Okay. Shall I stop here?
Yeah. Yes, Professor. Yeah.
Okay. Yeah, I will just stop my stop sharing, and then if anyone has question, I can definitely answer all the questions.
Yeah. Thank you, Professor. Thank you. It was a very informative talk. So you have briefly elaborated about 2D materials based flexible and wearable sensors, which is used for various medical applications like heart diseases and measuring body temperature, pressure, and as well as emotional detection. So really, I enjoyed this talk. So now I request a participant to interact with the Professor Latte.
Yeah, there are several.
If you want to ask any question, please unmute yourself. You can ask.
You can unmute everyone so that they can otherwise they will not
post the message in the chat box also.
Okay.
Hello.
Yes, Professor, you are muted. Hello,
okay.
Professor,
Yeah. Yes, someone is asking question.
Yeah.
Hello, I'm Meghna Merchant. Can I ask a question?
Yeah, please.
Yeah, sir, I would like to ask you, can you give me an example? How can I fabricate sensor?
So what kind of sensor you want to fabricate?
Gas sensor.
Gas sensor. Okay. So there are two ways. You can one way you can get this pattern ready-made from the market, and whatever nanomaterials or whatever materials you synthesize, you can coat that materials, and you
directly I can deposit it on the sensor.
Yes, directly coat. Otherwise, you have to do this electron beam lithography or lithography to fabricate the device, or you have mask, right? You can get the mask. These are readily available in the mask. You can put that mask on the substrate, and you can deposit the film. For example, you can deposit the gold film, deposit the silver film, platinum film, and you can take out the mask. You have a device in your laboratory.
By which technique can I deposit it on?
You can deposit by any, like maybe electron beam lithography or simple evaporator. You can use any evaporator where you can evaporate the gold, platinum, and all these things.
Okay. Okay, thank you.
Professor, there is one more question from chat box. What are the material source for making transparent sheets for nano generator? What are the material source for making transparent sheets for nano generator?
Okay, currently we are working on graphene and graphene-like 2D materials other than graphene 2D. That part I have not covered. So that is 2D inorganic layered material like MOS2, WS2, PTSE2, HFS2, HFAC2. Lot of range of materials are there. We are working on that. So they are real like application. Then there are a lot of, the property of nanomaterials, right? The moment you go less than 10 nanometer, right? The property completely changes. The color can change, color can tune. So come to a thickness or layer where material become completely invisible, right? Less than 10 nanometer. So that you can control. Yes.
Yeah. Professor, Dr. Pankaj Kumar.
Yeah.
Yes, sir. Thank you, sir.
Yeah.
Myself, Dr. Pankaj Kumar Singh from IIT BHU. Sir, your presentation was really nice.
Thank you.
My question is regarding the graphene. If we apply the PVD or CVD method, how this can be different in the synthesis of the graphene?
PVD, what technique you are using? You are using pulse laser deposition or because in PVD, right? Pulse laser deposition, right? So, in PVD, pulse laser deposition, you have continuous film, right? You are monitoring thickness here. In CVD, you will get this kind of triangular shape of this graphene layer, which are 100 micron in size, right? So here we can control the thickness, right? Here also you can have, in PVD we have film, right? Not a real kind of layers. You cannot take out layers. So this is a film. We need to take it out. So we know CVD there are a lot of defects. So once you can optimize or control the defects, because currently CVD based devices shows low mobility, low performance, because it has a lot of defects. Once if you can control the defects and all these things, the quality of the film, then really CVD will be better. But currently PVD kind of PLD based device or any other materials grown by PVD, they're really good because they have more control, more crystalline quality and all these things as compared with the CVD.
So which one will be the better one? PVD or the...
Yeah, PVD, you can use PVD because CVD, you will get very low mobility, low sensitivity, low selectivity because again, the kind of defect it has by the material grown by CVD. So you can use definitely a PVD based material or PVD based grown material.
Okay, thank you, sir.
Yeah, thank you, participant. So if there is no more question, on behalf of all the participants, once again, I thank to Professor Latte for his valuable and informative talk. Thank you, Professor.
Thank you.
Thank you, Professor Latte. You have given very excellent talk to our participants. Participants have given very excellent feedback. This will be very useful for the scholars and academicians who are pursuing or doing the research in that 2D nanomaterials as well as the pertinent applications, the technical applications. Thank you so much, Professor.
Thank you,
Professor. Thank you. Dear participant, there is a feedback in the chat box, so kindly fill it. So the next session will start at tomorrow, same time 11 a.m. So kindly join on time. Yeah, thank you. Participant, you can leave now.